A phenomenon first detected in the solar wind may help solve a long-standing mystery about the Sun. Why the images from the Earth Orbiting Interface Region Imaging Spectrograph, aka IRIS, and the Atmospheric Imaging Assembly, aka AIA, show evidence that low-lying magnetic loops are heated to millions of degrees Kelvin. Researchers at Rice University, the University of Colorado Boulder and NASA's Marshall Space Flight Center make the case that heavier ions, such as silicon, are preferentially heated in both the solar wind and in the transition region between the Sun's chromosphere and corona. There, loops of magnetized plasma arc continuously, not unlike their cousins in the corona above. They're much smaller and hard to analyze, but have long been thought to harbor the magnetically driven mechanism that releases bursts of energy in the form of nanoflares. In the NASA-funded study, which appears in Nature Astronomy, the researchers describe brightenings in the reconnecting loops that contain strong spectral signatures of oxygen and, especially, heavier silicon ions. The team of Bradshaw, his former student and lead author Shah Mohammad Bahauddin, now a research faculty member at the Laboratory for Atmospheric and Space Physics at Colorado, and NASA astrophysicist Amy Weinbarger studied IRIS images able to resolve details of these transition region loops and The images allow them to analyze the movements and temperatures of ions within the loops via the light they emit, read as spectral lines that serve as chemical fingerprints. It's in the emission lines where all the physics is imprinted, said Bradshaw, an associate professor of physics and AST. The idea was to learn how these tiny structures are heated and hope to say something about how the corona itself is heated. This might be a ubiquitous mechanism that operates throughout the solar atmosphere. The images revealed hot spot spectra where the lines were broadened by thermal and Doppler effects, indicating not only the elements involved in nanoflares but also their temperatures and velocities. At the hot spots, they found reconnecting jets containing silicon ions moved toward, blue shifted, and away from, red shifted, the observer, IRIS, at speeds up to 100 km per second. The transition region is only about 10,000 degrees Fahrenheit, but convection on the Sun's surface affects the loops, twisting and braiding the thin magnetic strands that comprise them, and adds energy to the magnetic fields that ultimately heat the plasma, Bradshaw said. In that process, the magnetic fields of the plasma strands break and reconnect at braiding sites into lower energy states, releasing stored magnetic energy. Where this takes place, the plasma becomes superheated. But how plasma is heated by the released magnetic energy has remained a puzzle until now. The waves carried by the heavier ions are more susceptible to an instability that causes the waves to break and generate turbulence, which scatters and energizes the ions. This broadens their spectral lines beyond what would be expected from the local temperature of the plasma alone. In the case of the lighter ions, there might be insufficient energy left over to heat them. Our study shows for the first time that this is also a property of the transition region, and might therefore persist throughout the entire atmosphere due to the mechanism we have identified, including heating the solar corona. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.